Hi everyone, my name is Phil and I am a senior lecturer in astrophysics at the University of Lincoln. I want to use this video to basically give you a sample lecture. If you were going to basically come and study physics with astrophysics at the University of Lincoln, there are various modules that are on the astro part, and one of the lectures I'm going to give kind of in this video relates to one of those modules, and it's just to give you a bit of a sample of the sort of things you're going to learn on the degree program on one of those modules, so you've got a bit of a feel for what to expect. Really, it's going to be, I say, a random lecture. I'm just going to pull out a lecture of one of the second year modules for now on exoplanets and just see how you feel about that, basically. So we have this new program, Physics of Astrophysics, and I'm the program leader for that. And as part of that, we have various different modules. So we have Introduction to Astronomy, we've got exoplanets, stars, galaxies, all of those sorts of things. So if you're interested in the astrophysics part, then definitely check out this video and the sort of things I'm going to cover on it, which is going to be exoplanets. And that's basically my kind of area of research anyway. So the sample lecture I'm going to do today is going to be from the module, the second year module that you do on this particular program, which is the Solar System and Exoplanets. And if you want to get more information about the program and the modules at the University of Lincoln, then you can go onto the website and you can get an overview of it all there, basically. But the main aim of this particular module is to basically look at the solar system, challenge our understanding, really. So looking at real data, what we know about it, what we don't know about it, and then actually put it in the context of exoplanets. What are we finding with exoplanets? How do we actually find them? And anything we know about exoplanets and maybe want to know actually as well, and linking it to modern astronomy and how the observations are actually made themselves. So this lecture I'm going to give in this video here is going to be lecture 18. So it's going to kind of be midway in the actual module itself, and it will be called Exoplanet and Planetary System classes. So up to this point, we would have learnt about different sorts of planets, the solar system, and now we're moving on to exoplanetary systems and a way in which we can actually classify them. So we can have multiple planetary systems, but there are different sorts of planetary systems, and this is what this lecture is actually going to cover today in this video. So this is all taken from the Exoplanet archive. If you haven't visited that, it's a great place to kind of keep up to date with current detections of exoplanets, and even ones that I've got a signal but they've not been fully confirmed. And I've just pulled a plot off that basically, and it shows the number of detections of exoplanets over the years. And if you're not familiar with exoplanets at this point, an exoplanet basically just means it's a planet orbiting another star that's not in our solar system, basically. And up to date, and it depends when you're watching this particular video, but it's over 5,000 now. And it's probably approaching 6 or so. Maybe when you watch this video, it's at 10,000. It all depends. It depends when the data is released, what survey telescopes are being used, but sometimes you get a massive spike in discoveries because there's been lots of data released. So here you basically got the cumulative amount, and at the moment, I believe it's under 6,000. It's between 5 and 6,000. So we've got loads and loads of planets detected so far. Now, most of those planets can be classified in one way or another. So if you look at the populations of exoplanets, they will typically fall in one of these sorts of groups or one of these classes. They could be a hot Jupiter, cold gas giant, ocean world or ice giant, more rocky planets and lava water. There's various different types of planets, and most of them will fit into one of these sorts of groups. So what we're going to do for the first part of this lecture is kind of define what those groups are, basically. What makes a hot Jupiter? What makes a lava world? Okay? So again, going back to the Exoplanet archive, you can pull lots of plots off of real data, which is what I've done for this lecture. And this plot I've got here is the mass of the confirmed planet in Jupiter masses. You can do it in Earth masses if you want. But because a lot of the planets discovered are big, massive planets, it makes more sense to do it in Jupiter masses, unless you were looking at Earth-like planets. And then along the bottom, it's the orbital period. You can do that in semi-major axis instead, or other parameters, but I've done it in mass and orbital period because we can get a good feel for kind of the system that way. So those are our detected exoplanets, confirmed ones, and the top green box that I've put there, they aren't planets, and as you can see, there aren't any planets in that particular area. Once you get above around about 13 times the mass of Jupiter, they start to fuse deuterium. Now, that basically means that they generate energy in their core. They're not at the right core temperature to be a star, but they sit in between a planet and a star, and that then means they're classified as a brown dwarf. So above 13 Jupiter masses, they are typically a brown dwarf. So you're not going to see any planets there because, again, they're starting to generate energy in their core at this point. Now, the minimum mass for a giant planet is around about 10% the mass of Jupiter, so 0.1 times the mass of Jupiter, and that goes up to about 13. So you've got this range here, which I've kind of denoted with the blue box. Anything above 0.1 Jupiter masses, they're typically composed of more than 50% hydrogen and helium, which means they're a gas giant. So gas giants sit in this bracket here because at that point they're typically mostly composed, or the majority composed, of gas, hence the name gas giant. And they can exist anywhere on the orbital period range. It's defined mostly here by their mass. You've got the upper and the lower limit. Now, hot Jupiters obviously sit towards the left-hand side. They have very short orbital periods. Now, you're probably looking at the colour boxes I've used here and thought, oh, that's a little bit odd. Why have I used green for very hot and red for warm? I haven't got a good answer for that, if I'm honest. Anyway, so really close to the star with the very short orbital periods. You're talking orbital periods pretty much less than 1 day. These are ultra-short period planets. And these are big planets, so these will be very hot Jupiters, essentially. There's not that many of them. It's quite rare to get them so close to their star, basically. And then, typically, you get the next bracket, which are our hot Jupiters. They're ones you've probably heard of the most. These are short period Jupiters, so again, big gas giants. And orbital periods are going to be on the order of days, so you're talking like 3 to 9 days, really. And they orbit their host star around about 10% the distance of the Earth-Sun distance. So again, very close to their star. That's why they're very hot, but they're also very big, so hot Jupiters. And then you've got your warm Jupiters. These may exist kind of around the orbit of Earth and a bit closer. So you're talking 9 days and above orbital periods, up to, kind of around where Earth is, essentially. And these are warm Jupiters. These are not hot, but they're kind of warm. So we've got those. We can essentially split out our hot Jupiter into these sort of 3 brackets here due to their temperature. They occupy the same sort of mass distribution though. Now, most of these hot Jupiters have been detected with the transit method. And maybe you're aware of the transit method. That's when a planet passes in front of the star, blocks out some light. Now, unfortunately, if we're looking at a star and we're looking for the star to dim down because a planet's passed in front, there's a bias there. If that happens more often and with a bigger dip in brightness, it's easy to detect. So initially, hot Jupiters were most of the planets that were discovered. So we had this bias in hot Jupiters in the known discovered population of planets. However, now that our telescopes and our equipment is getting better, our techniques are better, we're detecting a broader range of planets, and actually these hot Jupiters are not as prolific as we once thought. It's more of an observational bias originally due to the transit method. So now we're left with the opposite side of the gas giants. These are going to be cold Jupiters. These are ones that are located much further away. And most of the time, because these have they have very long orbital periods, we don't detect them with the transit method because we've been waiting years for it to just pass once in front of the star. So instead, these are mostly detected with the radial velocity method or directly imaged because they're now far enough away from their star that we can actually directly image them. They're also very big. So a big planet obviously is brighter, so we can actually see it easier. Now, another interesting thing, at least observationally, is if we find cold Jupiters orbiting a star, we quite often find that they are accompanied by inner super Earths. So these are planets that are bigger than Earth, but they are inwards of the cold Jupiter. I suppose if you think about it, not that dissimilar to the solar system. We find that Jupiter is essentially cold. We're not a super Earth, but we are inwards of that. So this is a statistic that seems to crop up a bit. Inner super Earths typically accompany cold Jupiters, which is interesting. Why they're there? How do they form? Now, on to the next category then is our giant planets and ice giants. These typically might be referred to as Neptunes or Neptunian-like, because Neptune and Uranus are not true gas giants. They're denser. So if we were to actually map out the radius as a function of the mass, they would sit somewhere between water and hydrogen and helium. So they're not gas giants and they're not dense kind of terrestrial planets. They sit somewhere in between density-wise. And on the period mass plot, they kind of exist this sort of area here. Now, the ice giants are going to be further out, obviously, because they're going to be cooler, but we can still get hot Neptunes that are very close to their star. They're just close, a bit like the hot Jupiters, essentially. And then we have this group of sub-Neptunes. This is a group that exists between the size of Earth and the size of Neptune. Now, it can be defined as a planet that has a smaller radius than Neptune, but it might actually have a bigger mass. It could be denser than Neptune, but its radius is smaller, so it's a sub-Neptune size. Or it could be a planet that has a smaller mass than Neptune, but it might have an enormous radius. And it could actually even be up to the size of Jupiter. Well, actually, that's not true because it's we're talking sub-Neptune, but that would be a puffy planet. And again, these can be hot, warm, or cold, but the ones that have low mass, high or big sizes are typically known as like super puffs or puffy planets because they're puffed up, they're quite low density. So your super puffy planets exist here, and actually there are a few we've detected so far, and they have very, very low density. So you're talking about 2% that of Earth. Now these planets have got masses that are only just more than Earth, yet their radiuses can almost be up to Jupiter, so they're really puffed up. Now, why might that be the case? Why are these planets puffy? Why are they inflated? Well, part of the reason could be they could be close to their star, so they could be kind of puffed up from the atmosphere being blown away. But we'll come back to that. Now, super Earths sit on the bottom end, really, of the sub-Neptunes. They're closer to Earth, really. These are compact rocky planets. They're not low-density planets. These are essentially terrestrial planets, and they can have masses of 2 to 10 that of Earth. They're typically quite small radiuses. So super Earths have radiuses less than 2 times that of Earth, whereas a sub-Neptune is typically going to be between 4 and 2 times the radius of Earth. Now, I know on the slide here I've got 1.8, but there is a radius gap here, so there doesn't really seem to be anything that exists around about the 1.5, 1.8, which is a bit bizarre. I don't know why is that the case. Now, back on with super Earths. When we calculate their density, so if you know their radius and you know their mass, you can get their density. Now, Earth-like ones are quite rare. When you do that, you can work out whether it's a purely land planet, a mixture like Earth, or an ocean world. What it's telling us actually, the ones we're detecting and discovering, the vast majority are actually kind of land planets that have very little water on. Earth-like planets are actually very rare. So they only make up about 1% of the Earth-like or super Earth planets that we're finding. And then about 19% are ocean worlds. So the vast majority of them are more just land-based, essentially, if we calculate their density anyway. So exact copies of Earth are very rare. So Earth-like planets, compact rocky planets with a mass that's quite similar to Earth is quite rare. And these would have a radius of about 80% to about 120% that of Earth. Now Kepler 186f is quite close. It's a planet that's quite close to Earth in kind of size and that, but they're very rare. We don't find many of these actually, which is intriguing. Like, why is that the case? Are we struggling to detect them, or are they just not there? So these are questions that need to be answered a bit later on, or active questions that we're working towards. And then we've got lava worlds. So lava worlds are rocky planets that have the majority of their surface as molten lava. Now, interestingly, Earth was a lava world early on in its formation. So when Theia, which was like a Mars-sized planet, collided with the young Earth, it would have left the newly formed Earth as a lava world until it cooled down. And actually, in the formation process, there's a lot of heat involved. So very young planets are quite likely to be lava worlds. But if we find a terrestrial planet very close to its star, then it's quite likely that that could be a lava world as well, because it'd be so hot that the surface is essentially scorched by the sun or the star, and it melts the surface. And then we've got these ocean worlds, which can be Earth-like or super Earth-like, basically. And it will be classified as an ocean world if about 75% of its surface is water. So most of these have a significant fraction of water in them. Now, interestingly, if they are a significant fraction of water, deeper down in the planet, the pressures could actually compress that into ice. So it could be compressed into ice deeper inside. Again, you've got another example there of Kepler 138d that's potentially one of these ocean worlds. And another interesting statistic that comes out from our observation is that about 40% of red dwarf stars, which actually are the most common star in the universe, have super Earths. So if we want to look for life, for potentially Earth-like worlds, red dwarf stars are a good start. That's pretty handy since most stars, or the vast majority of stars, are going to be red dwarf. Not the vast majority, but they are the largest majority of population of stars there are, and a lot of those have super Earths. So that's a good statistic. Now, going back to this sub-Neptune super Earth aspect, there is this really unusual bimodal distribution in their sizes. So if we were to plot the number of planets against their radius, so again, we've got a plot on the right-hand side there, you've got its bimodal distribution. So you basically got two peaks and there's a gap in between. There's a deficit in planets around about 1.5 times the radius of Earth. There doesn't seem to be a lot of planets there, and it's known as the sub-Neptunian radius valley because it's like devoid of planets there. So what we do find is that we have a group of super Earths between 1 and 1.5 times the radius of Earth. We then also have a second group which are like sub-Neptunes. These are around about 2 to 3.5 times the radius of Earth, but in between 1.5 and 2, there's this deficit of planets. Now, it could be that we just haven't detected them, or there's another process occurring there which is depleting planets in that particular area. Now, interestingly, there is a process that can deplete it. So what happens is, if your sub-Neptunes get close to their star, so let's say they've migrated inwards, again, this is another video entirely, and actually we would have covered planetary migration at this point anyway, that planets can migrate when they're forming in a disk. So if they start out as a sub-Neptune, bigger radius, bigger puffed up atmosphere, they move inwards close to the star, and then what happens is the star actually evaporates the atmosphere, and then they become a rocky terrestrial planet with the rocky core remains left over in the center. So what that basically tells us is this radius valley in the middle is quite time sensitive. They don't spend a lot of time at that radius. So when we go and sample our systems out there, they very quickly evolved through that process. So we're finding very little at that particular size. So this is a process that could deplete that population of planets. Now, Now we've covered kind of the planet classifications or the different sorts of planets. We're now going to have a look at the planetary system classification. This is where we've got multiple planets in a system. And they can be put into one of four groups. They can be anti-ordered, ordered, similar, or mixed. And they make intuitive sense. You can look at those and go, yeah, that's anti-ordered, that's ordered, that's similar. But there is a proper method to classify them, which will work towards. So yes, you can visually do it. You can say they get bigger in mass as they get further away from their star. But there are some equations we can use to actually mathematically classify them properly. So it depends on their composition, size of the planet, and where it's located. Because you can basically do it with a variety of different parameters. Maybe you do it on radius, maybe you do it on mass, their density. It kind of depends really, but you're most likely going to do it in mass or radius or something like that because that makes most sense. So the first one is ordered. Again, makes perfect intuitive sense. Your planets get bigger in mass as they get further away from the star. So you start out with terrestrial planets close to the star. You then work towards your gas giants at the outer edge. So they get more massive as you get further away from the star. That's ordered. There's an order to that. Now, the observations that we make, they're generally biased against finding small planets a long way from their star. Why is that? Well, they're hard to detect. Again, a small planet, if it passes in front of a star, is only going to block out a small amount of light. And it will happen very, say, infrequent, but it takes a long time for it to go round on its orbit. So the chance of detecting one's quite rare. So what this basically means is that ordered is one of the most common architectures that we see. And that's most likely due to detection bias, not necessarily because that's the true representation of the actual system. So it can be ordered wise, it can be monotropic. So basically, it keeps increasing in size as it gets further away from the star, or it can be non-monotropic. So basically, it generally increases as you get further away from the star, but there are fluctuations within that. An example of that is going to be the solar system. The biggest planet in the system is Jupiter. That's not at the end, that's in the middle. But if you were to basically average it all out and calculate it mathematically, then it does show a trend in getting more massive as you get further out. So it can be increasing each time, or it can have some fluctuation, but the general rule is it will always be increasing as you got further out. Anti-ordered, that's going to be the opposite. This time round, you've got your big gas giants close to the star, and they decrease in mass as they get further away. So the planets decrease in mass as you get further away. Complete flipped around compared to your ordered one. Now, what might be causing that? Well, the more massive planets in the inner part of the system likely get there due to type 2 migration. Again, we would have covered migration prior to this lecture if we were doing it properly. And then the least massive planets at the outer edge likely get there due to a type 1 migration. Now, migration rates are different depending on the type of migration. So this could be why we end up with an anti-ordered system. It could be due to the variation in the migration rates. We then also have mixed. Again, fairly intuitive what this means. Mixed means that there's no real relationship between the mass and the distance. It's kind of randomized. You can have big planets and little planets anywhere in the system. It doesn't correlate to the distance from the star this time around. An example of that actually is GJ876. This has 4 known planets. What it has is it has 2 super-Earths or 2 sub-Neptunian planets, and they sit either side of 2 large Jupiter-mass planets around a red dwarf. To be honest, that's quite unusual anyway, having 2 Jupiter gas giants around a red dwarf. The three outer planets actually are in a Laplace resonance, which means that they orbit to some simple integer ratio of one another. So it could be like a 2:3 ratio, or one orbits once for every two orbits of the other. So this is an unusual system for many reasons. Two big planets that are straddled by two super Earths. That's a very unusual system, and that would be mathematically classified as mixed. And then the final one is similar. Again, makes sense what this is. This time round, all of your planets are fairly similar in size, composition, and stuff like that. There's no real change in their sizes or anything as you increase in distance or decrease in distance. They're all fairly similar to one another. Now, an example of that is actually TRAPPIST-1. Now, TRAPPIST-1 is a really exciting system for lots and lots of reasons. It has around about 7 rocky terrestrial planets, and a good proportion of those are in the habitable zone. These orbit a red dwarf star, but they're all fairly similar in size. They're all rocky terrestrial planets, so this would be a similar type of planetary system. Now, what I've kind of shown you really is we can classify from observations, but there's the other side, essentially, the theoretical side. And the Byrne model is a pretty full-on model which includes pretty much everything. So it includes the evolution of gas, planetesimals, the accretion of gas and solids by the young protoplanets, how they essentially interact with everything. And it's a theoretical model, really, a global model for planet formation and evolution. So we have a theoretical model, really, to predict how these planets form and end up where they are. We then also have the opposite side, which is what we actually see. And with lots of science, it's about trying to get the two to work together. Like, do the observations match our theories? If they don't, we need to go back and alter this particular model. So we can start to basically compare the architecture between the Byrne model and what we actually see. So observation-wise, on the left there, what you actually find is the number of systems you've got there, and how they actually change with regards to the where they sit. And on the right-hand side, you've got the observations compared to the predictions from the Byrne model. And there's a few different versions of that, which I'm not going to go into with us because it's not the main part of the lecture. And most of the time, they typically there's some correlation there. However, the biggest issue is with ordered. So the main difference between the observations we make and the theoretical model is the ordered architecture. And this is most likely due to observational bias. Remember what I said about the size of the planets? Big planets further away from their star are easier to find than small planets that are further away. So we're probably going to find observationally that we get more of those. It doesn't mean that our theory is wrong. It could just be due to an observational bias. They're easier to find, not necessarily representative. Now, some interesting things that kind of come about from what we've learned about these architectures is that the similar type typically have lower total mass of the system. So if you take all of the planets and the total mass of all the planets, a similar architecture is going to have a lower total mass than the other groups, which is interesting. And that suggests that in a similar scenario, a similar architecture, you just don't have the gas giants. There's no giant planets in them. They're mostly the smaller super Earths, rocky planets, things like that, maybe sub-Neptunes. Order type typically have larger total mass, so the opposite of similar. And this suggests that they do contain the big giant planets. Again, kind of makes sense. If they're ordered, they're getting bigger, you're going to end up with the bigger planets on the outer part. So ordered typically have larger total mass of the whole system. However, it is possible for both systems to have and not have giant planets, but as a general rule, these two things kind of stand out for us. Now, Again, it's just mentioning kind of like the fact that the ordered type shows the largest deviation from the Burn model. I'm not going to focus on this too much, but what they're basically doing here is they're just kind of plotting out the density of planets with regards to their radius, mass, things like that. And what you'll find is if you have a look over that, is that the one that deviates away from the Burn model the most is the ordered. And again, most likely, maybe, well, possibly from observational bias, but that is one thing that kind of crops up. So again, I'm not too worried about focusing on this particular part at the moment. But what we really want to do, so I've discussed the different types and classifications of system, which we could visually look at that and work it out, but there is a mathematical method to do that properly, and we can work out, because there could be some systems which are on the boundary. Like, we couldn't quite work out if it's mixed or if it's ordered, anti-ordered, stuff like that. So we can use some equations to help us there. Now, the coefficient of similarity measures the order of magnitude variation in some quantity q from one planet to another. And it starts from the inside and it moves out. And it's for a system of n number planets. Now, what you might do here is maybe use the mass. So what you do here is you basically divide the mass of this second planet from the star by the first planet from the star, take the log of that, and then you add that to the next one, then the next one, then the next one. And what you would basically find is if the planet system was ordered, then your coefficient of similarity should be positive because it would increase with each one. If it's the other way round, what you would find is that it would be anti-ordered. So this can give us an idea of whether it's ordered or anti-ordered. If it's zero, it means that they are basically going to be similar. So this can help us identify which way around that the actual variation is occurring. So it's a pretty useful tool to have. The problem arises from similar to mixed because they essentially cancel each other out. Each one that you do as you go out, they can cancel each other out. So you still end up with a coefficient of similarity of 0. So we need something else to distinguish these when it's not clear, basically. So what we then have is this coefficient of variation. Now, this is a descriptive statistic used to measure the magnitude of variation in a set of numbers. What does that mean? Well, we're basically just going to divide the standard deviation by the mean, and it should be a positive quantity. So basically, if they all have the same value, we expect it to be 0. And it doesn't really, the coefficient of similarity depends on the order of it, whereas the coefficient of variation does not. So it's two separate things that we can use in conjunction with one another to basically help us determine the class of the system. So mixed systems are typically going to have high values of coefficient of variation. That should make sense when you think about it. You're looking at the standard deviation. You're going to have a higher standard deviation where you've got a mixture of different sorts of planets, whereas a similar system would have lower values of coefficient of variation because they're all similar. Your standard deviation is going to be quite small. So again, this can help us then distinguish between these two, despite them still having the same value for the coefficient of similarity. Now, again, once you've calculated all those out, this can then help you determine what the architecture class is going to be. So ordered, anti-ordered is fairly straightforward. You're going to get positive or negative depending on how the ordering goes. But if it's borderline or it doesn't really, it gets quite close to 0, you're going to have to do the coefficient of variation. And then that's when you can then use it to determine if it's going to be mixed or similar. Now, a natural consequence of all of this is that you can't do it for a 2-planet system, which probably makes sense. It needs to be 3 or more planets in order for you to actually do this sort of calculation. Now, if we go to the solar system, and you can check this yourself if you want, if we run the numbers, essentially, we find that it's ordered. We get the coefficient of similarity to be 0.36, that's positive, that's ordered. and then our coefficient of variation is about 1.85. That would give us ordered. Now, if we were to replace Neptune in our system by a rocky terrestrial planet, it then becomes mixed. So it doesn't take a lot to tip it over to being mixed, because actually the solar system is not a perfectly ordered system. Again, as I mentioned before, Jupiter is the biggest planet and it sits kind of in the middle of the system. So it's not a perfect ordered system, but at least when we run the numbers in its current form, it does come back as ordered. In fact, if we only did the outer solar system, we might find it's probably anti-ordered, because it goes Jupiter, Saturn, Uranus, Neptune. That would be the other way around. So why is it actually important? Well, we can investigate some more things actually with regards to the architecture. If we have low metallicity stars and high metallicity stars, we can then look for things like the water content as a function of all the different systems. Now, what stands out interesting here is, regardless of the type of star that it's orbiting, anti-ordered are typically rich in wet planets. That's very useful if we're going to start looking for life elsewhere. If we find anti-ordered systems, they would be a good place to focus our searches. So anti-ordered typically have an abundance of wet planets, and by wet we mean that they have sufficient water content, essentially. And ordered are typically rich in dry. So again, we might want to avoid looking at ordered planetary systems if we're going to be looking for life elsewhere. Maybe we can focus on the other ones instead. And another interesting thing actually is the formation process. We have low mass disks and massive disks. These are the disks that planets form around the stars. Now, if you've got a very low mass disk where the planets actually form, then we typically end up with similar types of planets. That's probably because we just don't have the mass to form the gas giants, so we end up with a collection of smaller planets which are kind of similar in mass, size, and things like that. However, when we have massive disks, we've typically got more mass to form the bigger planets, so we typically end up with more ordered, anti-ordered, and mixed if we start out with a big disk where the planets form. So again, something interesting with regards to the formation process and what we end up with architecture-wise. So anyway, thank you for watching, and I hope you enjoy. If you have any questions about the program we run at University of Lincoln, then just drop me some comments, and hopefully, you enjoy. So thank you.